Okay, welcome everyone to this continuation of what is quantum topology. Today I would like to tell you about very super stuff. Literally super stuff. Super. If you don't know what that means, we'll see. It's kind of one of those. So I will say that right away. Super mathematics. Let's try to actually find that. Super mathematics. Super mathematics. Yeah, excellent. Super mathematics is actually something that does exist. And I always wondered, and we'll go into that in a second, it comes from physics, whether putting super in front of everything is actually a good or a bad idea. But we'll see. You should come to your own conclusion. I will tell you what super is and how is it related to monoidal categories. Right? So today I will show you a key example of a monoidal category. Diagrammatically, because that's what we do. So super mathematics. And as you can see, I'm also not sure whether you should spell it like this, super space mathematics, or like Wikipedia apparently spells it, just one word, super mathematics. I have no idea, it doesn't really matter. But super mathematics, now you can judge for yourself whether you like that name or not, essentially means Z mod 2 graded. And that essentially just means you give things a flavor, even or odd. You give things a flavor, bosons or fermions, right? You give things a flavor. And you have the usual rules that you would expect. Something like even times even is even. Even times odd is odd. Something like that. And you just give it a fancy name, super. So you give things a flavor, even or odd. And you give it a name, super, and then you can just repeat all of standard mathematics. You have Lie algebras, so you have super Lie algebras. You have groups, so you have supergroups. You have vector spaces, so you have super vector spaces. Excellent. And you have this whole language. You have super string theory, you know? You have this whole language where you just put a super in front, and apparently everyone knows what's going on. And yeah, that sounds really good. It's just very good strategy. So I think the iPhone kind of copied that strategy, right? Just put an I in front of everything. iPad, iPhone, iWatch, whatever, you know? Kind of the same idea. Super this, super that. Anyway, so the category of super vector spaces is literally just vector spaces, but now you can say a vector space comes in a flavor. This is not even an odd dimensional, this is really an extra flavor, like a spin or something, right? Something you add as an extra information. So a vector space can be even, or a vector space can be odd, or it can have 5 even parts and 3 odd parts, something like that. And I would like to describe this category diagrammatically. And yeah, I will just call it vect Z mod 2. I should just call it super vect, I guess. But I will just call it vect Z mod 2 diagrammatic. Okay, so hopefully that so far makes some sense. Super mathematics is a branch of mathematical physics, if you want, which applies the mathematics of Lie superalgebras to the behavior of bosons and fermions. This is literally where it comes from. So bosons and fermions, they're essentially the same. Here's something fun. So if you click in this way on the boson and fermion article and you just watch at this thing here, you essentially see that they're essentially the same because the text is essentially the same. The only thing that changes is this boson and this fermion, they swap places. So bosons and fermions are kind of two flavors of the same thing, right? And you want to put them in one theory, and this is where essentially super mathematics came from. Super mathematics. And if you look for images for super mathematics, you will find something like that. I probably should have expected that. So in some sense it's a good name, sometimes it's kind of a strange name. And I will just say Z mod 2, right? Even odd, you just give it a flavor. Okay, cool. And the way I will describe the category of super vector spaces is kind of interesting. Because it's a diagrammatic language that we will use several times to describe several very different looking things. The diagrammatic language of webs. So what is a web? This is a web. So here we go. This is a web. Here's a very beautiful. Here is a very beautiful. What is it? Square, I guess. 1 edge, 2 edge, 3 edge, 4 edges. Here is a 1, 2, 3, 4, 5, 6. Here's a nice hexagon. So this is a web. What you really see here is a cut through a soap foam. Yeah. So webs are literally everywhere in the real world, and I hope you get the name makes some sense. Why it's called a web, it's like a spider web. And mathematically, it's just a trivalent graph, right? Here, every vertex, let's zoom in. Here, every vertex is nice trivalent, so it has just 3 adjacent edges. Except that the boundary here, you have this one valent, just call that boundary, it's fine. So a web with potentially a boundary. It's a 3-valent graph, potentially has a boundary. And these will be these are the morphisms in supervector spaces. It's kind of very, very interesting. So webs are the morphisms in my supervector space category. And the way this works, and we are going to do several examples along the same line as we go along, here supervector spaces diagrammatically. So the objects are just, like for cobordisms, they're just boundary points. Yeah. So in our little picture up here, so here would be the object, there would be another object, kind of the same conventions. And the morphisms are webs, but you have those relations on them. So some relation to remove internal edges, which makes this category rather boring if you think about it, right? You can redirect here this internal edge, and some associativity relation. Whenever you see an internal circle, it's you can just take it out, and some isotopy type relations. And I really would like to think of this as a little bit more general, where I have any type of grading group. Turns out Z mod 2 is the most represented symmetry in real life. A lot of things are Z mod 2, right? So even, odd, whatever, a lot of things are Z mod 2, and very rarely you see more complicated groups of symmetries, more complicated symmetries. So either have no symmetry, that's a trivial group, or you have Z mod 2 symmetry. Very rarely you see additional symmetries. But in principle, we could do this for any grading group, where now our objects are just elements of the group, and they multiply as they should multiply. Why don't I need this in this description? Well, I only have 2 objects in Z mod 2. One of them is a trivial object, and I don't draw trivial objects. So, in reality, I just have boundary points, which is just really one object. But I could do that for any group, and I kind of wrote down the description, right? So G times G inverse should have a morphism to 1 because they should cancel out. Then you draw this little cup thing where the orientation essentially just tells you which one is the inverse. From GH, you should be able to go to GH, and here is our little trivalent vertex, and it's a multiplication. That's exactly why we have webs, why we have those trivalent things, because they're kind of a prototypical diagrammatic thing that mimics, or that is a blueprint for multiplication. Right, but you don't need to know that at the moment. You can just do it for any group if you want. So the objects are the group elements, and you would have this, and you would have relations with labels and whatever. Don't worry about it for Z mod 2, for supervector space. We don't need that. We just need these type of relations. And kind of the interesting thing is that I will make that more precise as we go along. We really want this description, this diagrammatic description. That this diagrammatic description is monoidally equivalent, so it is the category of supervector spaces if you would define them as vector spaces with a spin, with a Z mod 2 grading. And yeah, this is kind of nice. So I really just give a diagrammatic description of this category here, which is an algebraic object or linear algebra object, the category of supervector spaces, in terms of diagrams. The category of vector spaces would be this guy for the trivial group. Why? Well, for the trivial group, you wouldn't draw anything, would be very boring, and that's the category of vector spaces. So just the morphisms are just scalars, right? Or matrices of scalars. That's why I write matrices of scalars, right? That's why I write upon taking direct sums. The word sum is missing. Upon taking direct sums, which just really means, in this case, you have, like for vector spaces, matrices of things, but now your matrices can have an even or odd flavor to it. No? That's the real difference. Super mathematics, even or odd. Mathematics, trivial group, no additional information on the vectors or entries or scalars or whatever themselves. And that's really the difference. Yeah? And in this picture, one of them has diagrams and the other one has no diagrams, just the empty diagram. Anyway, so super is always like, as you could see it, right? The bosons and the fermions. And they're kind of the same. They kind of do all the same things. So a photon and an electron, they kind of do the same thing. I have no idea what a pion is. I have no idea. Doesn't really matter. I know what a photon is. I know what an electron is. That's probably where it ends. But also, what I know is that they kind of have the same behavior. So if you look at bosons and fermions, not in super mathematics, probably I can do something like bosons versus fermions. Yeah, for whatever. Well, the other way around. I actually don't care so much. And they probably have some things like this, right? So they have different spin, kind of behaves similarly, but this has kind of 0, 1, 2 spin. This is a half, 3/2, 5/2 spin. So they're not super different. They do some, I have no idea what that is. They do some kind of different type of behavior, but they kind of fit in the same theory, and this is where people developed this idea of super mathematics. Standard model of elementary physics. By the way, whenever we can't explain something, we invent a new elementary particle, I guess. So there are quite a few. So traditionally, you would think maybe this picture is enough here, where you have, well, maybe this one is better, where you just have electrons, protons, and neutrons. That's very nice, but it kind of doesn't explain everything. Maybe photon. Maybe photon is also traditional. But it's kind of nice, but it doesn't quite explain everything, so you kind of need to invent, in some sense, more things. The Higgs boson. The electron fermion. Whatever. Doesn't really matter. In math terms, it's really just a Z-mod 2 thing that you use to distinguish them. And as usual, if you have an extra type of flavor on something, it sometimes gets more interesting. It's somehow, a lot of the theory works in parallel. So whenever you see super mathematics, it's literally in parallel to standard mathematics. But then there are some interesting different types of behaviors. If you study Lie super algebras instead of Lie algebras, there will be some slight change in behavior, but most of the theory goes through. And of course, the changes are what makes the study of them interesting. Okay, but that was enough waffle about bosons and fermions. Probably shouldn't have done that, because I have absolutely no idea what these are. I just know Z-mod 2 graded. That's all I know. And the flavor I showed you is kind of very important. I really would like to stress that. So here are two different ways to present a group. My group is really just Z-mod 4. So I could write Z-mod 4 as a multiplication table. In this case, as an addition table, if you want. That determines the group completely. Or I could say there's a generator, and I just describe what the generator does, and that determines the group completely as well. So 1 is a generator, because 0 times 1 is 0. 1 times 1 is 1. If you do 2 times 1, so 1, 1, you have 2. And if you have 3 times 1, 1, 1, 1, you have 3. And the only extra relation you need to add is that 4 times 1 is again 0, right? 4 times 1 is again 0. So this would be 3 plus 1. 3 plus 1 is 0. Here you go. 3 plus 1 is 0. 4 times 1 is 0. Could illustrate it in a graph where the extra relation is just you go around this face. So this is, let's say, 0, and every edge means you add 1. From 0 you go to 1, from 1 you go to 2, from 2 you go to 3, from 3 you go to 4. So the relation here is just that it closes up a face. So these are two different ways to think about a group, yeah? Like multiplication table type, or generator and relation type. And this is exactly what we did. So a group given by multiplication table, that's like describing vector spaces or super vector spaces as an algebraic object. And a group given by generators with relation, that's like this diagrammatic description of the category. And the big goal of quantum topology is to find generator and relation description of nice categories. I probably should have also wrote here nice generator and relation descriptions of nice categories, right? Not an arbitrary one, not a complicated one, but actually a nice one. And I hope this one is pretty nice. So and kind of interestingly, we can copy that several times and describe several diagrammatic categories using this language of subforms of webs. But anyway, I hope you enjoyed this video, and I also hope to see you next time.